So chapter 2 is on random variable and operations on random variable. Can you see the material?
Yes, ma'am.
Yes, ma'am.
The lecture plan is the topics are introduction to random variables, notion of random variable, that means definition of random variable, events generated by random variables, and formal definition of random variables, axioms, and conditions. Now, the notion of random variable or definition of random variable, this part is known to you, right?
Yes, ma'am.
And then classification of random variables, discrete and continuous, probability distributions. Have you studied probability distributions, probability mass function, cumulative distribution functions, all these things?
Ma'am, I think we need a recapitulation. Then it will
So
take
this
some
part
time.
will be a recap part. So properties of PDF, then we'll discuss probability density functions, and we discuss a particular distribution, a very popular distribution known as Gaussian distributions. Then we'll go to the operations on random variable. So first comes expectations, then moments, different types of moments, variance, significance of variance. Then we'll discuss two inequalities which are very important. One is known as Chebyshev's inequality, and the second one is Markov's inequality. And we'll discuss moment generating functions, characteristic functions, moment generating functions, etc. And we'll end with this Chernov's inequality, the notion of Chernov's inequality and bound. So, introduction to random variable. What is the concept of a random variable? In noise like signals, we always deal with voltage, current, torque, etc. These are physical quantities, but random in nature. So, in this class, we are considering that this voltage, current, torque, etc. These are random in nature. So, this can be measured since these are physical quantities, hence, though they are random in nature, those can be measured in physical units. In these cases, the chance occurrences are related to real numbers. So we can specify at a particular instance, say we can specify the voltage as say X volt or current say Y ampere, like that. So we can measure in physical units with the help of physical units, and the chance occurrences are related to real numbers X, Y, so on and so forth. And in some other chance experiments, the outcomes are described in words like head or tail. In case of coin tossing experiment, the outcomes are either head or tail, even or odd, like this in case of a die. So in some other chance experiments, in contrast, the outcomes are numbers like 1, 2, 3. We can consider, for example, the throwing of a dice, and the number of dots will give us a value which is 1, 2, 3, 4, 5, 6, etc. So what we find that in some chance experiments, the outcomes are described in words like head, tail, success, failure, and in some other chance experiments, the outcomes can be specified with the help of real numbers. So what we'll have to do, we'll have to, by some means, we'll have to alleviate this ambiguity, and we'll have to have some formalization, mathematical formalization, with the help of which we can describe this situation as well as this situation. A single mathematical tool, a single mathematical formalization with the help of, we can describe this chance experiment having outcomes described with words like head, tail, or this chance experiment with outcomes which are simply numbers. And since this particular formalization, this particular tool is random variable. So notion of random variable, informal definition. A random variable is simply a function or rule that maps each and every point in the sample space onto a real line. That means numbers. So random variable is a function which will map the outcomes. Suppose this is my sample space, so these are the outcomes, okay? So a random variable will map each and every outcome in the sample space or each and every point in the sample space onto the real axis. That means with the help of that mapping function, we'll finally get some real numbers like 1, 2, 3, 4, 5, 6 in this particular case, for this particular example. So the assignment of those numbers is our own doing. How to assign the numbers, that we can decide upon, and could be almost anything. So for the above example, we have chosen the most common numerical assignment, that is the real number is equal to the sum of dots. So far, is this clear? Can you recall this part?
Yes, ma'am.
Yes, ma'am.
Next, let's discuss another definition. A random variable is a number x zeta. So from this expression, it's clear that x is a function of zeta, right? Just like we write f within brackets small t, where f is function of small t or time in that particular case. So with this representation, we can say that x is a function of zeta, and this we are defining to be the random variable. So a random variable is a number x zeta assigned to every outcome zeta sample point of an experiment. This is a little bit precise definition compared to the previous one. So from this expression, it is clear that you know what is a function. So it's clear that zeta is, in this case, the independent variable, whereas this x zeta is the mapping function, and hence zeta will be for each and every zeta in the sample space, will be getting a number on the real axis. So this number could be the gain in a game of chance, the voltage of a random source, the cost of a component, etc. So let's consider that the function fi, we define a function for a dice throwing experiment. So let's define the outcomes to be fi for I varying from 1 to 6, and x fi is given by 10i. That means fi is 10 into I. So when the value of I will be equal to 1, x f1 will be 10, x f2 will be 20, x f3 will be 30, x f4 will be 40, and finally x f6 will be 60. So this is another assignment or another rule or another function we can define in this manner also. Now the next definition, a random variable is a function whose domain is the set S, that means sample space, of all the outcomes of the experiment, and the range is the real axis. So when we define a function, we know a function does have its own domain and its own range. So the notion and definitions of functions, in case you know this, a function xt is a rule of correspondence between this independent variable t and the dependent variable x. Here t is not time, t is any general variable. So for when we use this representation, we know that this variable t is the independent variable. T is called the independent variable. The values of the independent variable t form a set st on the t-axis, right? So we can say that the values of t are basically the different outcomes of a chance experiment, and all those outcomes together form a set st on the t-axis. So this set is called the domain of the function xt. You have studied all these things, right? Hello?
Yes, ma'am.
Yes, ma'am.
Okay. Mhm. Should I skip this portion, or for maintaining the continuity, should I go through this section?
Ma'am, you can briefly go through it, ma'am.
Uh, the values of the dependent variable x form another set Sx on the x-axis, and the set Sx is called the range of the function xt. The rule could be xt is equal to t square, like that. So the notation xt or x zeta is often ambiguous. Why? It might mean either the particular value of x for a specific t. That means if we specify t, then what is going to be the particular value of x, or in general, xt can represent the general rule or provide us the mapping function. So for that, what is done to alleviate this ambiguity, often we drop this t or zeta and simply denote by x. The function is simply denoted by this x. The definition of a function can be phrased as we are given two sets of numbers st and sx. To every t belonging to this particular set st, we assign or get a number x belonging to the set Sx. So this leads to the generalization. We are given two sets of objects S alpha and S beta, right, consisting of elements alpha and beta respectively. Alpha and beta respectively, we say that beta is a function of alpha. If to every element of the set S alpha we can make correspondence to an element beta in the set S beta. So this concept has been shown with the help of this diagram. So this is the domain of the function where the different values of alphas are shown as alpha 1, alpha 2, alpha 3, so etc. And this alpha 1, with the help of that rule, with the help of that mapping function, the alpha 1 has been mapped onto this real axis, which is beta 1. Alpha 1 is has a correspondence with this particular value beta 1. So if we consider an example, say set of children in a community, S alpha is the set of children in a community and S beta set of their fathers, right? So alphas are the set of children in a community and beta basically denotes their father, okay? So one children will be assigned to one single father. So this assignment is correct. Similarly, a father can have two children. So another sample point or another point from this domain can be mapped onto the same point. So we can say that alpha 1 and alpha 4, they are siblings and they have the same father, right? But this assignment is not correct. So alpha 1 is one child and a child cannot have two fathers. So this assignment is incorrect, right? So what is the essence? So this one is another example, odd numbers. So we are assigning a value 0 and these are the even numbers and we are assigning a value 1. So different sample points from the sample space are mapped onto the same number on the real axis 1, 3, 5, 0, whereas 2, 4, 6 are being mapped onto this particular point 1. So we can conclude that different sample points or set of them, that is events, set of sample points are events. Events may be mapped onto the same sample point on the real axis, like this case. So the domain of the function consists of the 6 faces of a die for this particular example. Its range, however, has only 2 elements, namely the numbers 0 and 1. This is important, that is xt or beta alpha. So these functions should be a single valued function. So what is meant by single valued functions? For a specific value of t is equal to t1 or alpha is equal to alpha 1, we should not get two values of x, that is either x1 or x2. For two different values of alpha or for a single value of alpha, say alpha 1, we should not get two betas like beta 1 and beta 2. So this is one condition, that the function has to be a single valued one, which is required for random variable. So events generated by random variable. So in the study of the random variables, the question of the following form may arise: what is the probability that the random variable x is less than a given number x, or what is the probability that x is between the numbers x1 and x2? Now, before assigning the probability, or before ascertaining the probability, before determining the probability, first of all, let's try to understand what is meant by this representation. So x is the random variable. X is less than equal to a certain value. That is the first part of the question. And the second part of the question can be mathematically represented as x1, x greater than equal to x1 less than equal to x2, like that. So that means the random variable x will lie between two numbers x1 and x2. So this is basically a representation of an event. Let's look at this particular table. So these are the sample points. These are the sample points, zeta 1, zeta 2, zeta I, etc. And these are the values of the random variable, possible values of the random variables. The random variable x can assume these values for different zetas. So x zeta 1, x zeta 2, x zeta n. So x less than, what was the expression? X less than x. So from this table, if we can find out the values from this rightmost column, if we can find out the values x zeta i's which are less than small x, that means what we are doing, we are actually collecting the number of the events or the outcomes in the sample space So we are trying to find out the number of outcomes, or we can say the number of events for which the value of the random variable is less than this particular number which is given by x. So the random variable x less than equal to x will actually denote all the experiment all the outcomes or all the events for which the random variable x will assume a value which is less than x. Am I clear?
Yes, ma'am.
So the left column shows the list of zeta i's. These are the sample points on S. The right column shows the corresponding values or numbers of x zeta I of x. So given any arbitrary number x, we find all numbers this that do not exceed x, and thereby we try to find out the collection or set of events which satisfy this condition. So this is important. Thus, x less than equal to x is not a set of numbers, but a set of experimental outcomes or set of events. And that was the second part of the question. The meaning of x greater than equal to x1 less than equal to x2. So it represents a subset of S consisting of all the events or outcomes zeta such that this condition hold. Clear? So that means again from this representation what we are getting a set of events, and here x1 and x2 are two arbitrary numbers, and this notation x equal to x is subset of S consisting of all outcomes zeta such that x zeta is equal to x. That means probably we'll get one event. So for that particular example, xfi is equal to 10i, that was the rule. So the set x, the random variable x will assume a value which is less than equal to 35, will give us three events, collection of three events. That means I can vary from 1 to 2 to 3. So we'll get three events because for 1 we'll get 10, 2 will get 20, and 3 will get 30, right? So three events will get a set of three events or three outcomes. This set x less than equal to 5 will be an empty set. Will be empty or not empty set, will be empty or null set, as there is no outcome such that xfi less than equal to 5. And for this we'll get two events, again 2 and 3, I guess. So for the next condition, the set x equal to 40 will give us one single event. That means f4 has occurred. Again, x35 will be a null set. I guess I don't have to elaborate on this. So formal definition of random variable, axioms and conditions. A random variable x is a process of assigning number x zeta to every outcome zeta. Already we have learned this. The resulting function must satisfy the following two conditions, but is otherwise arbitrary. So what are the conditions? Conditions for a function to be a random variable. Random variable may be almost any function we wish. We shall, however, require that it's not multi-valued. That is, every point in S must correspond to only one value of the random variable. So the first condition is that the set x less than equal to x be an event for any real number x. So we'll be able to define such an event on the sample space. And the probability of this event is denoted as probability x less than equal to x. That means what is the probability of that particular event? denoted by x less than equal to x and defined on the sample space. The second condition we require is that the probabilities of the events x equal to infinity and x equal to minus infinity will be 0. So the rule, the mapping function could be any function, any arbitrary function, but the conditions are the function should be a single valued one. Events could be specified for a random variable. Events could be specified on the, or can be defined on the sample space, and x is equal to infinity and x equal to minus infinity, the probabilities of both this should be equal to 0. So this is the pictorial representation of the previous example. Just look at this figure and I think you'll be able to understand this. And this is a convention. A random variable is denoted by a capital letter like capital X. Classification of random variables, discrete and continuous. So discrete random variable. A discrete random variable is one having only discrete values. That means x can assume only discrete values like 0, 1, 2, 3, like that. So in a coin tossing or die throwing, result is a discrete random variable. If the head is assigned a value which is equal to 1, and if the tail is assigned a value, say, which is equal to 0, that means in coin tossing experiment, we'll get the random variable will be discrete in nature. Similarly, in dice throwing case, simply consider that the range is 1, 2, 3, 4, 5, 6, or it could be 10, 20, 30, whatever be the case. The associated random variable will be discrete in nature. Now, the sample space for a discrete random variable can be discrete, can be continuous, or can even be a mixture of discrete and continuous point, right? The nature of the random variable is discrete, and we can have a discrete random variable from a discrete sample space, or from a continuous sample space, or from a mixture of discrete and continuous point. Now, from a discrete sample space, it's quite obvious the sample space is discrete in nature. The outcomes are 1, 2, 3, 4, 5, 6. And if you consider this particular example, so it's obvious that from a discrete sample space, we'll get a random variable that would be discrete, certainly be discrete in nature. So here the mapping function is resulting into two possible values. One is 0 and the other one is 1. And hence the random variable is discrete. So if the sample space is discrete, always will get a discrete random variable. But from a continuous sample space as well, we can have a discrete random variable, and that depends upon how we define our random variable for that particular chance experiment. How we assign a value, or how we define the range corresponding to this domain for a particular chance experiment. So let's consider this example. This point can be conceived as 12 odd zeros. So these are the points. So wheel of chance, we can rotate this. So this is called a wheel of chance for a continuous wheel of chance for a continuous sample space. But So you see, if I rotate this wheel, I can have any value like 12.001, 12.0001, right? So if I can measure precisely. So the sample space, the outcome of this experiment, denoted as wheel of chance. So the sample space can be conceived to be a continuous one, right? But we can define a random variable which is discrete in nature on this continuous sample space. How? If the outcome lies between these two values 0 to 6, 0 to 6, we assign the or we denote the range to be equal to -1, or say, for if the outcomes lie within this range, then we assume that the value of the random variable will be equal to 1. And if the outcomes lie within this range, then let's assume that the value of the random variable will be -1. So since the random variable can have two possible values, which are +1 and -1, hence we can say that the random variable is discrete in nature, right? Though the sample space is continuous. Now, the second one is continuous random variable. So far, do you have any question?
No, ma'am.
Now, continuous random variable. A continuous random variable is one having a continuous range of values. So the values will be in continuum, right? So in contrast, a continuous random variable cannot be produced from a discrete sample space. So a continuous random variable can be produced from only a continuous sample space. It cannot be produced from a discrete sample space because of our requirements that all random variables be a single valued function of all sample points, right? Since the function should be single valued one, hence a continuous random variable cannot be produced from a discrete sample space. And similarly, a purely continuous random variable cannot result from a mixed sample space because of the presence of the discrete portion of the sample space. Mixed sample space means part of the sample space is continuous and part of the sample space is discrete in nature. Now let's consider this example. Suppose the temperature at some geographical point is modeled as a continuous random variable capital T that is known to always exist between 10 degrees centigrade and 50 degrees centigrade. So temperature variation of the city is from 10 degrees centigrade to 50 degrees centigrade. So a continuous random variable is a random variable that can assume continuum of values in an interval either finite or infinite of real numbers for its range. So example of continuous, this is one example. The other examples of continuous random variable are electrical current, length, pressure, etc. Now in the example of the temperature of the city, let's make the non-realistic, okay, forget this term for the time being, make the assumption that all values in the range 10 to 50 degree are equally probable, right? So under this particular assumption, we argue that if we apply the relative frequency notion of probability, then and we assume that values t of t that fall in a small range dt. So we count those values of t temperature which falls within the small range dt within the range, within the interval 10 to 50 degree, centered anywhere in the range 10 degree to 50 degree. So from relative frequency notion, the probability could be found like this. dt is the range of temperature that we are considering, or we are trying to find out the probability for which, and the overall range is, the total range is 50 to 10. So this will give us dt by 40, right? So this is going to be the probability that the temperature will lie within this range. Now, the probability of any single temperature within dt. So if we try to find out a particular, um, the probability of occurrence of a particular temperature, then this gives the relation with the help of which we can find out the probability. And if you want to find out the probability of single temperature, then dt should tend to 0. There should not be any interval. The interval should be 0, right? Because we are trying to find out the probability of a single temperature. So we cannot consider any interval. So since dt tends to 0, hence the probability will be 0. Okay. So this is our conclusion. This example serves to demonstrate that the probability of occurrence of any discrete value of continuous random variable is 0. So with the help of this example and with the help of this simple derivation, we have come to this conclusion that probability of occurrence of any discrete value of continuous random variable is 0. So do you have any question?
No.
Now, probability distributions and probability mass functions, PMF. The probability distribution of a random variable x is a description of the probability associated with the possible values of x. So if we assume that x can assume, in a particular chance experiment, s can assume different value. X is the random variable, and the random variable can assume different values like x1, x2, x3 with probabilities pi, p1, p2, p3, etc., etc. Then the relationship of x and p, or the correspondence between the probability and the possible values of the random variable, that description is called the probability distribution. So for a discrete random variable x, the distribution is often specified by just a list of the possible values of x along with the probability of each. So we can list the values of x and we can list the values of the corresponding probabilities, and hence that will give us the distribution pattern, how the probabilities are distributed. Now, in some cases, it's convenient to express the probability in terms of a formula or with the help of a graph. So again, let's consider one example. So there is a chance that the bit transmitted through a digital transmission channel are received in error. So in a digital communication system, so we do have a transmitter which will transmit some digital symbols, and the digital symbols will be passed through a channel, and finally the symbols will be received by the receiver lying at the other end of the channel, right? So the channel actually joins the receiver to the transmitter. So the function of the transmitter is to transmit any symbol or any code word, and the function of the receiver is to receive those code word. Just to make it simple, to make it very simple. Okay. Now, when the receiver actually receives the transmitted symbol or code word or signal, whatever, what happens? Generally, the channel introduces noise. So because of the noise, the symbols or the bits which are being transmitted by the transmitter through the channel might get corrupted. right? So at the receiving end, a bit error can occur. What is a bit error? Now, let's assume that the transmitter has transmitted this 4 bits. This is one code word or one symbol. We can call it a code word. This 4 bits together, we can call it a code word or a symbol. So 1011. So let's assume that the receiver receives a symbol which is 1010. That means the receiver has interpreted this 1 to be a 0 because of the noise or because of some interference, etc., etc. Because of very many reasons, this particular bit might get changed, might get corrupted, and at the receiving end, it might so happen that the receiver interprets this 1 to be a 0. So that is basically a bit error. And we say that the receiver is receiving the transmitted signal with some error. Is this clear?
Yes, ma'am.
So since the code word consists of 4 bits, so what are the possibilities that the receiver will receive the code word with 0 error, with a single error? An error can occur at this bit, an error can occur at this bit, an error can occur at this bit or at this bit. So with a single error or 2 errors, 2 bits might get corrupted and will be misinterpreted by the receiver. So the number of bit received with an error could be 0 or 1 or 2 or 3 and 4. And you see all this in a single transmission, all these events can be specified like the bits the receiver has received the code word with error, with 0-bit error, with 1-bit error, with 2-bit error, like this, right? So these are the events, and you see all these events in a single transmission are mutually exclusive. So based on the model of the errors, let's assume that probability that x is equal to 0. So we assign a random variable x, and in this case we know that the random variable x can assume values, discrete values, certainly, which are 0, 1, 2, 3 and 4. So based on this, on the model of the errors, let's assume that the random variable will assume a value 0, and probability of that is given by 0.6561. Probability x equal to 1 is equal to 0.2916. Probability x equal to 2, it's 0.0486, and so on and so forth. These are the other two probabilities, right? So we can draw a simple diagram. So along this axis, we are plotting the points. That means the points, that is, the random variable can assume which possible values. The random variable can assume values like 0, 1, 2, 3 and 4. So this is the axis, and in this particular axis, in the y-axis, we are plotting the probabilities. So the probabilities that the random variable will assume a value 0 is given by this value 0.6561. So the probability that the random variable x will assume a value 1 is given by 0.2916. So this is the value when the random variable, this is the probability when the random variable assumes this value 2, and this is the diagram, right? So with the help of this simple diagram, we can represent the relationship between the probabilities of the probabilities that a random variable can assume a particular value and the values of the random variable, possible values of the random variables. So this is also another example of discrete random variable loading at discrete points on a long beam. So for a discrete random variable x, the distribution can be specified by a function that specifies the probability at each of the possible discrete values of x. Now, probability mass function, actually what we have drawn in the previous figure, that actually gives us the probability mass function. Okay, let's try to formalize this. So definition: for a discrete random variable x with possible values x1, x2, xm, a probability mass function or PMF is a function such that wxy, this w is the probability mass function, wxi is equal to probability that the random variable x can assume a value xi, right? So in the previous diagram, exactly we plotted this particular relation. So the previous plot actually gives us the probability mass function, or we can say that this condition should be held, that is wxi is equal to, we know that by definition, probability that x assumes a value which is equal to xi, and that should be greater than equal to 0. We know that the value of the probability always lies between 0 and 1. And also summation of, if I put a summation over here, summation of all the probabilities, that is I varying from 1 to m, so wxi will give us the summation of all the probabilities where x can assume all these values x1, x2, x3, and we are adding up those probabilities, and this summation will give us a value which is equal to 1. So these two conditions will have to be satisfied. So we can check this. We can, if we compute W0 plus W1 plus W2 plus W3 plus W4, we'll get a value which is equal to 1. Clear?
Yes, ma'am.
Next is cumulative distribution function. Cumulative means we should proceed, must proceed, and in the process, while we proceed, we'll go on adding up probabilities. So for the above example, we might be interested about the fact that what is the probability that up to 3 bits, that is 3 bits and fewer, that means at most 3 bits, are erroneous. At most 3 bits are erroneous. So if we want to find out the probability of this, that means we are defining an event which is x less than equal to 3. That means the random variable can assume values which are either equal to 3 or less than 3. The random variable, if you ask this question and if you try to find out the probability of this, then the random variable, we should not consider those values of random variable which are greater than 3, right? Now, the set of the events x less than equal to 3 is the union of the events x equal to 0, x equal to 1, and x equal to 2. Oh, sorry, x equal to 2 and x equal to 3, less than equal to 3, right? So x probability that x will be less than equal to 3 will be equal to, since the events are mutually exclusive, hence this will be given by probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2 and plus probability x equal to 3, and from those values of the probabilities we'll get the probability that x will be less than equal to 3 to be equal to 0.9999, right? I have not checked this value. The value will. So following this approach, we can determine the value when the discrete random variable assumes a particular value, that means when x equal to 3, from the knowledge of this kind of distribution functions, that means if we can find out the probability px can assume values which are less than equal to 3, and p probability that x can assume values which are less than equal to 2, then subtracting this probability from this probability, we can ascertain the probability that the random variable x will assume exactly the value which is equal to 3. So probability x equal to 3 can be obtained from this probability x less than equal to 3 minus probability x less than equal to 2. Is this clear?
Yes.
So it's established that sometimes it's useful to consider another distribution such as probability x less than equal to x, right? So previously we were interested about the distribution that probability of the random variable x is exactly equal to some value x. Now we are trying to find out the probability such that the value of the random variable will be less than equal to a value which is given by x, right? And now we'll try to establish the relationship between the random variable and the probability of the random variable defined in this manner. So such probabilities can be used to find the PMF of discrete random variable. This is one instance of PMF. So from this knowledge, from this distribution, we can find out the PMF as well. So the cumulative distribution function, or CDF, can be defined as, in general, for any discrete random variable x with possible values of the random variable capital X equal to x1, x equal to x2, x equal to xm, which are mutually exclusive, and if x1 is less than x2, is less than x3, is less than xm, then probability x less than equal to x will be equal to the sum of the probabilities where the sum is wxi and xi. This value should be less than or at best equal to x. So sum of these probabilities where xi is varying like this will give us the cumulative distribution, right? And this is equal to summation of pi where xi is less than or at most equal to x. So this is the cumulative distribution. This is basically the definition of the cumulative distribution. So this is defined as the cumulative distribution function, or CDF, of a discrete random variable x, and is denoted as fx. We use capital F to denote cumulative distribution, and the precise notation is fxx. This x is the random variable, an abstraction of this random variable, instance of random variable capital X, and this x signifies that x, the random variable, will assume values which are less than equal to x. Now for ease of or for convenience of for notational convenience, often we drop this x and we assume that the random variable is denoted as capital X, right? So be it fx or be it fxx, it signifies that it's equal to probability that the random variable capital X will assume values which are less than equal to this value small x. So this is nothing but the summation of all these probabilities where xi will vary like this, or summation of probabilities. We can represent this as pi, because Wxi is nothing but the probability mass function and can be denoted as Pi. So note, even if the random variable x can assume only integer values, the CDF can be defined at non-integer values as well. Like we can compute the probability or cumulative distribution function, or the probability that the random variable will assume. In the previous example, we saw that the possible values of random variables are 0, 1, 2, 3, and 4. But with the help of this formula, we can find out that what is going to be the probability that the random variable will assume a value which is less than equal to 1.5. So this is nothing but this probability we can determine by adding the probabilities of these two events, that is, the random variable x is assuming a value 0 and the random variable x is assuming a value 1. Since x can have a value which is less than equal to 1.5, hence we can identify two events and we can add their respective probabilities to find out the probability of this one. So though the discrete random variable was assuming values like 0, 1, 2, 3, and 4, we can compute this. We can compute what is going to be the probability that the random variable will assume a value which is non-integer. So now we can draw this. Okay. So again, this is the axis along which we are representing, we are showing the possible values of the random variable x. So that's why this axis has been labeled as small x, and the random variable x for that particular example can assume values like 0, 1, 2, 3, 4, right? Now when the probability that x equal to 0, the event is x equal to 0, the probability we know that is given by 0.6561. Okay. Now the probability that x will be less than equal to 1. So how to get that particular value? The value will be obtained by adding the probability of this and the probability of this event, right? So the probability that x will be less than equal to 1 will be given by this plus this value 0.2916. So the value will be, probably the value will be 0.9477. So that is 0.6561 plus this value. I guess either this value is incorrect or this value is incorrect. Please check. You get my point? If I add this to, so it will be 7, I guess, right? So, so here we are getting a probability. At this point, we are getting a probability that the value of the random variable x is less than equal to 1. So you see there is a step jump at this particular point. There is a sharp discontinuity and there is a step jump, and the height of this jump is giving us the probability that x will assume a value which is equal to 1. Isn't it? So again, I'm repeating that within this range 0 to 1, it could be 0.75. X can assume a value, or rather the value of the random variable x is less than equal to 0.75 will give us only this single event. The value of x that is less than equal to 0.95 will again give us this single event. Hence, in this particular event, in this particular interval, the probability, we are plotting probability along this axis. This axis denotes fxsx, and we know that fx x is nothing but a probability. So this is the probability axis. So within this interval, the probability will remain constant. Similarly, within this interval 1 to 2, because already we have seen that the probability that x is less than equal to 1.5 somewhere over here is equal to 0.9477. So it will remain constant. The value of the probability will remain constant within this interval. But at the discrete points, that means at the values which the random variable can assume. So at those points, this plot will have a discrete jump, a step jump like this, and the height of this step will give us the probability mass function, that is x, the probability that the random variable x is assuming a value which is equal to 1. Again, at this point we'll get another step jump, and this height of the step will give us the probability that x is assuming a value which is equal to 2, or probability W2. Now, in that particular manner, at this point, when x is equal to 4, if I go on adding all these values, we'll see that beyond this point, from this point onwards, the probability will remain constant to 1. So this plot is nothing but the cumulative distribution, plot of the cumulative distribution function associated with a random variable, discrete random variable x. Have you understood this?
Yes.
Okay. From this particular plot, from this cumulative distribution plot, it's clear that already we have discussed there is a jump discontinuity at every discrete value of x. Here is a jump discontinuity, here is a jump discontinuity. The height of the discontinuity is the probability mass function wxi. This is p or wx1, this is p or wx2, so on and so forth. Often we shall call fxx just the distribution function. Actually, this is the cumulative distribution function. Often we refer to the distribution function, cumulative distribution function, as simply the distribution function. The argument x is any value or real number ranging from -infinity to +infinity. Now, let's come to the properties of the cumulative distribution function. So what are the properties? Remember, the cumulative distribution function is represented by fx, this small x. Now, this is nothing but a probability. This is nothing but a probability. So fx, or when the value of x will be -infinity, the probability will be 0. Why? Because this is nothing but probability x is less than equal to -infinity. Right? Impossible event, hence the probability will be 0. Right? Now, fx infinity, that means probability x is less than equal to infinity will be equal to 1. Since the probability x can assume a value which is less than equal to infinity, actually this gives us the sure event, and hence the probability will be equal to 1. So the CDF of total probability is equal to 1. So from this it's clear that, and also we know that since fx is probability, nothing but probability, hence its value can vary within this interval 0 to 1. That means probability that x can assume a value, the random variable x can assume a value x will lie between 0 and 1. Now, the next one is a very important property, that is fx x1 will be less than equal to fx x2 if x1 is less than x2. Actually, here we can omit this equal sign. So fx x1 will be less than fx x2 if the value x1 is less than equal to x2. Okay. And so here, this is, suppose this is x1 and this is x2. And since we are adding up the probabilities, hence, probability that the random variable x will assume a value which is less than equal to 1 is given by this. And probability that the random variable x can assume a value which is less than equal to 2, or rather x2, is given by this. And hence it's clear that since x2 is greater than x1, hence probability x that will be less than equal to x2 will always be less than equal to probability x less than equal to x1. Have you understood?
Yes, ma'am.
What I'm saying? Now this event, so this is one event, that is the random variable x is assuming a value which is greater than x1 but less than equal to x2. So that we can obtain with the help of this relation or property number 5, that is, this is equal to fx x2 minus fx x1. That means this, the probability of this event is equal to probability x less than equal to x2 minus probability x less than equal to x1. Okay. The sixth property is fxx plus is equal to fxx. So what is the significance? What is the significance of this property? Can you tell me what is the significance of this property? Anyone? Hello? Can you tell me the significance of this particular property? Fxx plus is equal to fxx. You don't have any answer. I'm showing you the cumulative distribution function. Now, can you tell me what is the significance of this particular property?
The probability of a point, if the probability at x is fx, then the probability of a point just after x will also be fx. Right? That's the, the cumulative
Is it?
distribution.
The cumulative distribution function is continuous from right. I'm making this particular statement. Am I right or wrong? The probability distribution function, this property actually dictates that the cumulative distribution function is continuous from right. Am I correct or not? I'm waiting for your answer.
Yes, ma'am.
So this is the point of discontinuity. This is the point of discontinuity. Here is a step like jump, right? So what will be the probability when the random variable x will assume this particular value? So that particular probability we can guess that probability if we move along this particular direction. So at this point, the probability could be this one, or if I move in this particular direction, then I can say that at this point the probability will be this one. Is it clear? Now, since fx is equal to fx plus, hence it's clear that the cumulative distribution function is continuous from right. So the corresponding probability will get if I move along this direction. Have you understood this? What I'm saying, is it clear?
Yes, ma'am.
Yes, ma'am.
So in other words, we can say that fx can never decrease with increase in x. Fx can never decrease with increase in x. So if you go on increasing x, the fx, the value of the cumulative distribution function or the probability will go on increasing. Again, we can say that fx is a non-decreasing function of x, and property 4 again establishes this particular fact, as I have explained. So what is the proof of this particular property? So property 5 states that probability x will have values larger than some number x1. Here is no equal sign. Okay, so the probability that this random variable x will assume a value which is certainly will be greater than this value x1, but will not exceed another number x2. The event is x greater than x1 but less than equal to x2. So the event x less than equal to x1, x less than equal to x1, and x varying within this range, x1 less than equal to x2. There is no equal sign, right? So these two events will be mutually exclusive in nature. The first event is the value of the random variable is less than equal to x1, and the second event is the value of x is greater than x1 and certainly less than x2. So we can say that these two events are mutually exclusive, yes or no?
Yes.
So the event probability that x is less than equal to x2 will be equal to the union of these two, right? We are trying to find out that the event is x less than equal to x2. So that event will be union of two events, that is, or two sets, that is x less than equal to x1 and x greater than x1 and varying up to x2, right? So this event can be said to be the union of these two sets, yes or no?
Yes, ma'am.
So since these two are mutually exclusive, hence the probability of the left hand side will be equal to probability of this event plus probability of this event, right? Now we are trying to find out the probability of this event, That means we are trying to find out the probability of this event. Hence, the probability of this event will be the probability of this event minus probability of this event, right? So after site transposition, we get that probability that x will be greater than x1 and will be less than equal to x2 is equal to probability x less than equal to x2 minus probability x less than equal to x1. And by definition, this is fx2 and this one is fx1, and hence the proof. Property 6 states that fx is a function continuous from right. So how to establish this mathematically? Let's define that h is greater than 0. You know all these things. Fxa is equal to limit h tending towards 0 fx a plus h. That means fx a plus. So that means the function fx is continuous from right. So this implies that at points of discontinuity, CDF or cumulative distribution function is equal to the limit from the right. Right? Now, properties 1, 2, 4, and 6. What was the first property? Property 1. Property 1 was that if the value of x is less than equal to minus infinity, the probability will be 0. That is the first property. The second property was the total probability will be equal to 1. This is the fourth probability. That means the function is increasing in nature. And this is the sixth property. So 1, 2, 4, and 6. These four properties are tested when, suppose, any arbitrary function gx is given. Gx is given, and if we want to find out whether gx is a valid distribution function or not, right, then valid cumulative distribution function or not. So to establish that, we'll have to test, for gx, we'll have to test this property, this property, this property, and this one. That means we'll have to find out whether the function, any arbitrary function gx, is satisfying this property, as well as this property, as well as this property, and this property. If the function gx fulfills all this or satisfied all these properties, then we can say that yes, gx is a valid distribution function. So please note that properties 1, 2, 4, and 6 are used as tests to determine if some function, say gx, could be a valid distribution function or not. So if gx is a valid distribution function, then it must pass all the four tests. Clear?
Yes.
Jump discontinuity and the height, already we have discussed this. If x is a discrete random variable, often the discrete random variable is written in this form and a continuous random variable is written as CRV. Consider if x is a discrete random variable, consideration of its distribution function defined by the equation fx is equal to probability x less than equal to x, right? Here is it. Less than equal to x shows that fx must have a stair step form as shown in the previous figure. Staircase kind of a pattern or stair step form. And the amplitude of a step equal the probability, and the amplitude of a step equals the probability of the occurrence of the value x where the step occurs. We have discussed this, I think, You won't find any difficulty in understanding this. Now, this function or cumulative distribution function having this nature, these are the step jumps. So this can be mathematically represented in a more precise form with the help of this equation. So the cumulative distribution function fx is nothing but sum of all the values that a random variable x can assume. That means I is varying from 1 to n. So probability x is equal to xi multiplied by the unit step applied at x equal to xi. So if we add this unit step function to the definition of the cumulative distribution function, then precisely with the help of this particular example, precisely we can explain the stair-step kind of discontinuity or jump discontinuity present in a cumulative distribution function for a discrete random variable. Am I clear?
Yes, ma'am.
So you know, so in a shorthand notation, if this is written in this form, then this can be represented in this particular form, pxi u x minus xi, and we are summing for all the discrete values that the discrete random variable can assume. Next, let's consider one example. Now we are coming to the continuous random variable. So let's discuss continuous random variable with the help of an example. So a machine cuts extruded copper into lengths of approximately 5 meters. So a machine cuts extruded copper into lengths of approximately 5 meters. So we know that the length could be 5.01 or 4.99, 4.999 even, if we can go for precise measurement. And hence the associated random variable is assumed to be continuous in nature. Right? So a machine cuts extruded copper into lengths of approximately 5 meters using random sampling. A quality control engineer measures 50 of these lengths as from 4.95 meter for around 4.95 meters. Suppose 4 number of specimens or samples could be found, having a length which is equal to 4.97, approximately 4.97 meter. Suppose the quality control engineer has found 10 such samples, 4.99 meter, 20 such samples, 5.01, 12 such samples, and 5.03, 4. So total, these are the sample size, different sample size, and the sample sizes are not constant, and the total total population is 50. 4 plus 10 plus 20 plus 12 plus 4. And from this we can compute the probabilities considering a discrete random variable. So probability that x will be exactly equal to 4.95. You know, if x is conceived to be a continuous random variable, already we have discussed that we cannot find out the probability of a continuous random variable assuming a specific value. That we have already seen. But for the time being, we are assuming that the random variable, we are defining a random variable which is discrete in nature, and the random variable x is assuming a value which is exactly 4.95. So what will be the probability of that? 4 divided by 50, isn't it?
Yes, ma'am.
So similarly, if we assume that the x is assuming a value which is exactly 4.99, 4.99, then we can find out the probability in this manner. Now let's assume that the sample space consists of samples having length ranging from 4.94 meter to 5.06 meter. 4.94 meter to 5.06 meter, that is the sample space. And we are assuming that the random variable x now can assume any value within these two values. That means 4.9594 meter to 5.06 meter. So now we are grouping the data set. That means we are taking the lengths to be having this interval 4.94 to 4.98 meter, then 4.98 to 5.02 meter. You see 4.98, 4.98. So continuous the intervals. The first interval is ending at this particular point, and the second interval is starting from that particular point only. 5.02 and 5.02 to 5.06 meter. So could you please note down these values? 4.954, 4.97, 10, 4.99, 20, 5.01, 12, and 5.034. Have you noted down the values? Have you noted down the values?
Yes, ma'am.
Okay. So these are the ranges. So 4.94 to 4.98 to 5.06 to 5.02 to 5.06. Now just look at this histogram. Since now you have the value, I guess you will be able to plot this histogram very quickly and tell me whether the histogram is correct or not. So these are the values, number of samples, and these are the associated probabilities. Is it a correct histogram?
Yes, ma'am.
Okay, so I think I don't have to explain this histogram. Now, if we go on, if the sample size increases and if group width decreases. So if I decrease this group, this is the group width. So if I just decrease the group width, then what will happen? In the limiting case, this histogram will be a continuous one like this. So the histogram can be approximated with the help of, we can get rid of the step jumps, okay, and the histogram in a limiting case, when the group size is very small, group width will be very small, very small, then this histogram can be approximated with a curve, continuous curve like this. Am I clear? So under this condition, if the sample size increases and group width decreases, then the histogram approaches a continuous plot. Do you agree?
Why the 5.06 point are at horizontal line? I mean the X line. What is given?
5.06.
Yes,
That is the length of the sample. And the random variable, we have defined the random variable which can assume different length of the samples. So in the discrete case, you see, in the discrete case, which is easy to understand, X is a random variable, discrete random variable, which can assume a length which is equal to 4.95 meter. Right? Now we are decreasing and we are assuming that, you see, the sample space consists of the points ranging from 4.94 meter to 5.06 meter. And we are assuming that X, the random variable X, can assume any value within this range, within this interval, 4.94 meter to 5.06 meter. Right? So in the discrete case, so these are the values of X along this horizontal axis. That means the random variable X can assume a value of length which is equal to 4.94 or 4.98 or any value within this interval, or 5.02 or 5.06, because now we have assumed that our random variable can assume any values from 4.94 to 5.06 meter. That's why we have plotted 5.06 on this particular axis, on the horizontal axis. And in the vertical axis, along this axis, we have just shown the numbers, and along this axis, we have shown the probabilities. So along x-axis, we know that always we plot the values of the random variable, possible values of the random variable x, be it continuous or discrete. Now is it clear? Is the answer clear?
yes, ma'am.
So that's why this point is on this particular axis. So just a moment. So if I consider the discrete case, then this would have been this staircase kind of a plot would have been the cumulative distribution function for the random variable, discrete random variable x. Right? Already we have seen that if the random variable is discrete in nature, then the cumulative distribution function looks like this kind of a staircase kind of a plot, isn't it?
Yes, ma'am.
So now from discrete random variable, again, if you go on decreasing the width and if you go on increasing the sample size, and from the discrete case, if we try to come to the notion of continuous random variable, then we can say that this step-like distribution function will now be a continuous curve like this. So for a continuous random variable, the distribution, cumulative distribution function will be a continuous curve like this, and at this point after 5.06 the value will be equal to 1. So it will saturate, it will increase like this. Can you follow the cursor? And finally it will saturate at a value which is equal to 1. The probability will be equal to 1, as the total probability is always equal to 1. So for a continuous random variable, the distribution function or the cumulative distribution function can be plotted like this. So along this axis, we are plotting the random variable, which is continuous in nature, right? And along this axis, we are plotting the probability, that is the probability that x, the value of the random variable, is less than or equal to a certain value given by x. So far, is it clear?
Yes, ma'am.
Okay. So in the next class, we'll start from this. We'll discuss probability density function, and after that, we'll discuss some advanced topics. So if you don't have any question, then can I close this file?
Yes. ম্যাম আমাদের সেকেন্ড পার্টটা কবে থেকে শুরু হবে কিছু?
একটু রেকর্ডিংটা অফ করে নিই।